When we looked at terminating decimals like 0.55, we could easily write that as a fraction. Just in the name of how we say that number, 55 hundredths, we know it's 55 over 100. But what about a decimal like 0.5 repeating? We saw examples where fractions turned into these repeating decimals, so it would make sense that we should be able to take some of these repeating decimals and turn them back into fractions. And we totally can. All we have to do is follow a short process. Start by assuming that the repeating decimal is equal to some rational number like x. So we'll start with 0.5 repeating is equal to x. Then we're going to multiply that equation that we just created by powers of 10. In this case, we're going to multiply just by 10 on both sides. The reason why we're going to multiply by 10 in this case is because 10 times 0.5 gives us 5.5 repeating. Notice that the repeatend, which is just the digit 5, now appears completely to the left of the decimal, in addition to the repeatend with the repeating bar still appearing on the right. Remember that 0.5 repeating is equal to 0.555 forever. And multiplying that by 10 simply moves the decimal once to the right. So that would look like 5.5555 repeating, which we know we can write as 5.5 with a bar over the repeatend. So step one was create that original equation that takes the repeating number, the repeating decimal, and sets it equal to some unknown like x. And you can use whatever letter you want. I like to use x. Then step two is to multiply that equation you created by 10, sometimes maybe 100, sometimes 1,000. It all depends on how long your repeatend is. Doing that creates a second equation. In this case, that equation looks like 5.5 repeating is equal to 10x. We're going to use these two equations to eliminate the repeatend to the right of the decimal. To do that, I'm going to stack my two equations together. So I have 5.5 repeating is equal to 10x, and I have 0.5 repeating is equal to x. So I've got the original equation on bottom and the multiplied equation on top, and I'm going to subtract them. And the reason I'm going to subtract them is because that will eliminate the repeating part of the decimal, the 5 bar. So when we line these up, we see 5 repeating minus 5 repeating. They're in the exact same place value. They're equivalent in value, so one number subtract the identical same number gives you 0. And then 5 minus 0 would leave us with 5. Copy our decimal down. Notice that we have 5.0. This is no longer a repeating decimal. And then this is equal to 10x, take away 1x. If you have 10 and you remove 1, that leaves you with 9x. Now we have 5, which we don't need to write 5.0. We can just write 5 is equal to 9x. At this point, all we do is solve for x. Remember that x is the rational number that we're looking for. So we need to solve that equation for x. Right now, x is being multiplied by 9, but if I divide both sides by 9, I can isolate x, because 9 divided by 9 is 1. And my final answer says that x is the rational number 5 divided by 9. And if we were to type 5 divided by 9 into our calculators, we would in fact see that it's 0.5 repeating. We're going to do another example, but before we do that, I want to just walk through the steps again. First thing you're going to do take the repeating decimal, set it equal to x. Then you're going to multiply that equation by powers of 10 until you can have an entire repeatand on the left of the decimal. We're going to subtract those equations to eliminate the repeatand so that we can solve for x and get a rational number, a fraction with a numerator that's an integer and a denominator that's an integer. Let's take a look at the repeating decimal 0.235. So 235 is the repeatand, and it repeats in that pattern indefinitely. So our first step is to create an equation where we let that original number, the original decimal, be equal to x. Then I need to think about that decimal number. If I were to write this out without that repeating bar, it would look like 0.235235 continuing. I know that the repeatand is the digits 2, 3, and 5. So multiplying by 10 only moves the decimal once. I need the decimal to move 3 times. So instead of multiplying by 10, I need to multiply by a power of 10, like 10 cubed, because 10 cubed will move the decimal 3 places. So the second equation that we create would be our first equation multiplied by 10 cubed. Because 10 cubed times our repeating decimal would look like 235 point the repeating 235. We know 10 cubed is equal to 1,000, so we could write on the left-hand side, instead of 10 cubed times x, we can write 1,000x. Now we've created our two equations that we can use kind of against each other to eliminate the repeatand. So I'm going to put my second equation that we created on top because those numbers are bigger than the numbers that we started with. And then I'll put my first equation on bottom. I'm going to line up my decimals so that they're in the same place value. It'll make it easier for us to do our subtraction. Now remember, when we're subtracting equations like this, we subtract the left-hand terms. So 1000x minus 1x would be 999x. And then on the right-hand side, it's the repeatands that cancel each other out. So 235 repeating minus 235 repeating, that eliminates the repeating part of our decimal. And then the whole number part, 235 minus 0, that's still 235. Notice that the equation we just created has no repeatand notation because we've gotten rid of it. So we have 999x is equal to 235. Now we solve for x. We do that by dividing both sides by 999. And our final answer, well, let's be careful calling it a final answer. We do have a rational number now, but we should always check to see if this will reduce. 999 has very few factors in it, so let's start with that. Let's factor 999. That's going to be 9 times 111. 9 is 3 times 3. 111 is going to be divisible by 3, so 3 goes into 111. Let's just use our calculator here. 37 times. 37 is actually a multiple of 9. Just kidding. It's 36 is a multiple of 9. Let's see. 7, so not divisible by 2, not divisible by 3, not divisible by 4. I think 37 could be prime. Even if it weren't prime, the only thing that would make this useful is if 235 was divisible by 37. And calculator says it's not. We could check our other factors. We have 3 factors of 3. So if 235 is divisible by 3, then we can reduce it, and it's not. So this is actually the simplest form of a rational number that would be equal to the repeating number 0.235 repeating. So again, just to clarify, 0.235 is exactly equal to the fraction 235 over 999. Now maybe you're seeing a connection here or a pattern. When we looked at the number 0.5 repeating, it turned into 5 over 9. 0.235 repeating turned into 235 over 999. It's almost like the denominator is always going to be a 9. Now, that's not always true, but there is a pattern that's happening there, so if you notice that, right on. But let's take a look at a similar example that's slightly different. This number is in fact a repeating decimal, but there are digits in this number that do not repeat. The 2, the whole number part, does not repeat, and I can tell because it's not under the repeating notation bar, as well as the 3. That is not underneath that repeatand bar, so that number 2.345 repeating, if I were to expand that out, it's just the 45 that repeats. Now this is going to make the process slightly different than we did in the last 2 examples. You will start off the same way. Let x equal the original number. But notice that if we were to just simply multiply this up until the repeatand shows up on the left side of the decimal, we need to move the decimal 3 times. So if we multiply by 10 cubed, our equation would look like 1000x equals 2345.45. The problem is, if I try to use these 2 equations against each other, it doesn't line up in a way that eliminates the repeatand. Look at our decimal numbers, 2.345 repeating. When I go to subtract the other number, I'll have 2, 3, 4, 5. Ooh, let me line those up better. Notice that the repeating digits are not in the same place values because of the 3, which means we need to fix that first equation. Well, not really fix it. There's nothing wrong with it, but it's not useful. So we're going to create a third equation. Started off with the first 2 steps being the same, but now we're going to add in one more step. We need a third equation that will allow the repeatands to line up. So we'll take our first equation and multiply it so that the decimal separates the non-repeating digits from the repeating digits. So in this case, we need to move the decimal once. So we'll multiply by 10. That will create 10x is equal to 23.45 repeating. Now the third and the second equations both have 0.45 immediately to the right of the decimal. Those will work great against each other. Now, when I go to subtract my two equations, I see that the repeating part of my digits are going to subtract off. So instead of having 0.45 repeating, we have 0.0. We do need to subtract 2,345 minus 23. And then we also need to subtract 1,000 minus 10. That's going to give us 990x. Now again, we've created an equation that no longer has a repeating decimal in it. We just have integers. We can solve this for x by dividing both sides by 990. Now in this case, I can see that both my numerator and my denominator are in fact even. So I know I can at least divide top and bottom by 2. There's a chance that we could divide this even further. We've already practiced simplifying fractions, so at this point, go ahead and just type this into your calculator, ask it to simplify. You'll get the simplified version of the same rational number, 129 over 55. So again, remember that there is a pattern that we noticed before, where the denominator was a bunch of 9s, but that doesn't always happen. So cool if you notice the pattern, but don't depend on it.